Hi, welcome to the very first day of the Chemistry of Fireworks project. Today we're starting Benchmark 1, Lesson 1 on the atomic model. So before we get started, I just want to make sure that everyone had a chance to take the pre-test for this project and create a folder in your Google Drive for all of the items that we're going to be using in this project. If you've not done that yet, please pause the video and go take the pre-test or make your folder now. Let's get started with today's warm-up. Today's warm-up should go in your warm-up paper, in your binders, and if you're at home, you can either keep track on your own line paper or a Google Doc. So go back to the entry event or think about the entry event and tell me why Boomtown City Council hired you. Remember, you are an employee of ProSafe Education Services, and you need to document this or go back to the entry event and write that down for today's warm-up. So in each day's agenda, you're going to see a link to my lesson plan document. Now, I've had a little bit of a situation with people turning these lesson plans in to the Dropbox and Echo. Under no circumstances do I ever want you to turn in my lesson plan. However, there might be some things linked in the lesson plan, like worksheets, that you will be turning in. Okay? Now, you can make a copy of the lesson plan from the agenda and put it in your project folder for reference if you wish, just to find it easily, if you don't want to go back into agendas to find things. And then you'll find this recorded workshop linked in the agenda for each day that we have a workshop, and it will also be linked in the project briefcase. So let's click on this lesson 1 document and take a look at it together. So today's lesson is all about the model that we have for atoms. And we want to talk about the entire history of the atomic model. I'm going to be going into the slides shortly and doing a workshop on the atomic model. There are 2 graded activities, and this lesson does take 2 days. You're going to be doing vocabulary, which is best done on this Google Doc using your textbook. However, you can look up definitions online. And then following this video on day 2, you're going to want to do the Webquest. And there will be lots of things in this video to help you in the Webquest as well as your book. And then after each lesson, you'll see a reminder to do an update in the team management log. And because I'm recording everything ahead of time and posting lessons, you can go on to the next lesson. The workshops will be available for you for lesson 2 as well. So the slides are very helpful. We want to talk through some of these slides together before you do your vocab. And I like to start with this lesson because it really gives you some perspective on how people discovered atoms. As you know, atoms are invisible to the naked eye, and it's just in recent history that we've had microscopes powerful enough to look at the atom itself. So I want you to also think today about why this project is relevant. Project-based learning is supposed to connect you in some way. And, you know, this whole project on chemistry really revolves around fireworks, and we can learn a lot about chemistry through fireworks. But I want you to think about, you know, how many people and communities celebrate with fireworks each year, how important that is to some families or communities. Think about how local fire departments are involved with people's use or misuse of fireworks. Um, how much do you think the average person knows about the chemistry behind fireworks? Most people know that you light a fuse and they go boom, and that's the extent of it. But there's really a lot more involved for a firework to go off. And finally, think about how increasing the knowledge of chemistry of fireworks may possibly decrease the number of accidents that occur each year with fireworks. So just some things to think about as we get into this project and dive right in. So you might want to get right into the fun stuff. Let's blow stuff up. Let's start studying fireworks right now. What's inside of a firework? But really, we need to start at the very beginning of chemistry, which is to study the atom. That is the single smallest part of studying chemistry. So benchmark 1 is all about atoms and elements. And we're basically studying matter in its smallest form. And we will be studying the elements, the periodic table, and we'll get a baseline for what we need to know before we start benchmark 2, which is all about the reactions. There are a lot of great videos. I'm planning on showing you the crash course video in day 2. There will not be a video showing that. So if you'd like, you can click on the slides and watch this video on atoms tomorrow. And that will also help you with the Webquest in day 2's assignment. So this is the part where I'm going to talk a little bit. This is my workshop on the history of the atom. So the atom was first named by this Greek guy. Isn't he a lovely looking dude? His name was Democritus, and the Greeks were known for their philosophy, for thinking, and they theorized that if you cut something in half and half and half and half and half enough times, that eventually you would get to a piece that you couldn't divide anymore. And the term atom comes from the Greek word atomos, which simply means indivisible. So, for instance, if you took a piece of cheese and you cut it up, eventually you would end up with just a really, really tiny piece of cheese. They didn't understand anything about the components of matter or different kinds of atoms and elements. They just knew that there must be a smallest piece. So, this is, more than 2,000 years ago. Fast forward to the early 1800s, John Dalton, who's kind of known as the father of chemistry, wanted to know more about these indivisible atoms. And he actually did a lot of chemical experiments and determined that atoms come in all different sizes. For instance, he was able to take water, which is H2O, and break it down into its two components. He could isolate hydrogen and oxygen in their gaseous forms, and he found that oxygen was 16 times heavier than hydrogen. So he envisioned atoms as these different sized marbles, and he thought of them as just, solid spheres. Now we get into some of these scientists that came, more than 100 years after Dalton, and it's really a good idea that you take a look at their models in the textbook or do a Google search so you can see what these models look like. Hopefully, you'll do that more in your Webquest. But along comes this guy named J.J. Thomson, and he kind of built off of Dalton's model in that atoms were solid, but he noticed that they had both positive and negative components. And being a British guy, he likened it to plum pudding. Now, your book uses the muffin model because I don't think a whole lot of American students really know what plum pudding is. But imagine the muffin is like the positive, and the little negatives are the little cherries or berries scattered throughout the muffin. So he built upon Dalton's model and he said, there's more to it. There's these positive and negative components, and we're going to come up with a different model. Rutherford worked with Thomson. He actually did a really cool experiment. Google it if you'd like to know more about it. It's called the gold foil experiment. And he determined something quite odd about atoms, which is still true today, that they're mostly empty space. He was able to shoot a positively charged particle at a thin sheet of gold foil, and he noticed that most of these positive particles just went right through the foil, but every once in a while it would be repelled or bounced back out when it hit the positive center of the gold atom's nucleus. So Rutherford said, the atoms were mostly empty space. The solid part in the middle is the positive, which we now call the nucleus, and the negatives are just kind of floating around in this empty space. Niels Bohr built on Rutherford's model, and he kind of thought that the nucleus was the center and that the negatives didn't just float around, they orbited. And his model is still what we use today to help students understand atomic models and structure. It turns out that electrons aren't that consistent. They don't orbit the nucleus like the planets orbit the sun. But it turns out that that's really the best way to help students understand something as abstract as atomic structure. And I like this guy at the end, but wait, there's more. This guy named Chadwick was able to determine, based on measuring atomic masses, that there was something else in the nucleus. He actually discovered the neutron, which has no charge. And because it had no charge, it was one of the last things to be discovered. but we now know that both protons and neutrons make up most of the mass of the atom, and electrons are nearly insignificant. They weigh very little. So I just spent all of this time talking about all these dudes and their models. Oh, they're all mostly wrong. It's true. Although they built on one another and certainly some really important things were discovered, it turns out that the most modern model, the cloud model, is now what we consider the most accurate description of what an atom looks like. Now, this was created in the early 1920s, but several scientists contributed to it. The two that are credited with it are Schrodinger and Heisenberg, and they're talked about in the crash course video we'll watch tomorrow. So they basically said, yes, there's a nucleus. It's in the middle. It is positively charged with neutrons inside, but the electrons don't orbit. They simply exist in clouds, and they're kind of like shells. Think of those Russian nesting dolls, where one is inside of the other and inside of the other. And they said, you can't tell precisely where an electron will be, but you can give a best guess in the general area of where it will be in terms of distance from the nucleus. So you might say in this first shell, there might be 2 electrons hanging out in this area, and they don't ever go any further than this first shell. They just kind of hang out in this cloud. Then you might have another ring or shell of electron space where 8 more electrons might be hanging out. So these two kind of get credit for the cloud model, and this is what's considered still to this day, almost 100 years later, the most accurate depiction of an atom. Now, since then, we found all kinds of tinier pieces inside atoms. And if you check out my atom poster in the classroom, you can see that there are even smaller subatomic particles than protons, neutrons, and electrons that we've discovered. So if you haven't already, these are your vocabulary words that have been placed in a Google Doc for you. It's very important that you do those vocabulary words. They're going to be important for the entire benchmark. And let's take a look in our lesson plan at the second activity. The Atomic Model Webquest gives you a chance to review the scientists that I just talked about. This is best done online because I'm asking you to cut and paste various things from the web. And there'll be 2 different drop boxes, one for the vocab, one for this. And don't be afraid to just copy and paste this whole thing into the Dropbox and Echo. So these names should look familiar. We just talked about them. You're going to need to get an approximate year or country of origin. You can put in a picture of the model or just describe what some atomic particles were known at the time. Positives are protons, negatives are electrons, and the little O here is a neutron. Are any parts of this model still current in the modern model? And what part of this model was basically thrown out or discovered to be inaccurate? And I would like you to keep a running tally, if you would, of your URLs that you went to, so I can kind of see where you found this information. So every once in a while, I find a really good website that you guys have dug up. So please note that when you are finished with lesson 1, you will need to turn in the vocab here and the Webquest here. And this video will be posted in Echo. It'll look kind of like this for you to go back and look at if you'd like a little bit of a recap on some of those scientists. So this is the end of Benchmark 1, Lesson 1's recorded video. If you have any questions, don't forget to email me.